Okay, so this is our fifth lecture in this series, semester 4, Poisson Distribution. So, first of all, I will define what is Poisson Distribution. A discrete, a discrete random variable x is said to have Poisson distribution with the parameter mu greater than 0, if the PMF of x is of the form Px mu e raised to minus mu into mu raised to x divided by x factorial, where x ranges from 1 to 3 etc. Okay. So any random variable, a discrete random variable that has a PMF of the form e raised to minus mu raised to x divided by x factorial is called a Poisson distribution or Poisson random variable. So here mu is something we know. It's mean, right? Mean we denote mean by mu. So there is some why we are using mu is there is something is there. So I will discuss that later. And so now Poisson distribution as a limit. So actually, suppose we have a binomial distribution B, X, and P with the N and P. P is probability of success and N is number of trials. If N is very large and P is very small, in such a way that NP approaches a value mu, that means mu equal to NP, and this must be greater than 0 because we know that mu is greater than 0. And in such a way that NP approaches 0 and also we want mu greater than 0, then binomial distribution actually tends to Poisson distribution. So when is binomial distribution tends to Poisson distribution? When n is very large and p is very small. So that means if we know that the properties of binomial distribution, so there must have only two possible outcomes, success and failure, and the occurring of these outcomes are independent, and P is probability of success and Q is probability of failure. And if all these four conditions are satisfied by a distribution, and if n is very large and p is very small, then a binomial distribution satisfies a Poisson distribution. So in a binomial experiment in which n is large and p is small, then binomial bx and p is actually approximately equal to px mu, where mu equal to np. That is why mean mu is np, that is mean of a binomial distribution. Or now we can apply this when n is large. So n, if n is greater than 50 and mu is less than 5, n into p is less than 5, then actually we can use np is less than 5, then actually we can use Poisson distribution instead of binomial distribution, because calculation of binomial distribution is somewhat tedious. So now I will do a problem. A publisher of a non-technical books takes great pains to ensure that it's free from typographical errors, so that the probability of any given page containing at least one such error is 0.005. So the probability of having an error in a page is 0.05. That means p is here very small, and errors are independent from page to page. So there is only two possible outcome. One is either there is an error or there is no error. Now what is the probability that one of the 400 pages, so here n is 400, right, will contain exactly one page with error. So number of possible number of trials is 400. That means there are 400. Now here S denoting a page containing at least one error and F an error-free page. Okay, so S is success. Success means a page containing at least one error, and F is a page free from error. And here this follows a binomial random variable because n is very large, and binomial random variable with n 400 and p 0.05, therefore np is 2. So here np is 2, that is less than 5, and n is greater than 50, therefore it actually tends to Poisson distribution. So now first thing is we have to find out probability of x equal to 1. That means number of pages that contains error is 1. Then we can either use binomial distribution or Poisson distribution. So if we are using binomial, B1400.005. So that value, if you calculate, this is equal to p of x equal to 1 in binomial. This is actually n is 400 C1, p is 0.005 all raised to 1 into 1 minus 0.005 all raised to 399. So if you calculate this, you will get this value 0.270669. And if I am using Poisson distribution, p of x equal to 1 is actually e raised to, here np is 2, therefore mu equal to 2, e raised to minus 2, 2 raised to 1 divided by 1 factorial. So this calculation is easier. And their error, that means these two values probabilities are almost the same. So we can use, instead of binomial distribution, Poisson distribution. Now if you want to calculate p of x less than or equal to 3 in Poisson terms, this is actually p of x less than or equal to 3 means p of 0, p of 1, p of 2 plus p of 3. That is p of x less than or equal to 3. Now actually this is a Poisson cumulative distribution, and now we can use Poisson table. So either we can calculate this or you can use Poisson table. Poisson table is available in our textbook. I will show you that this is Poisson table, and here, okay, here p is, here np mu is 2, and x is 1. So we will check. Mu is 2, so this is mu value 2, and x is 1. This is x values, right? So 1, 2, 0.406. Sorry, x is 3, right? X is 3. P of x less than or equal to, so mu is 2. That is 0.57. Answer is 0.57. So I think the answer is 0.857. This is answer, right? 0.857. That is same as here, 0.857. Or you can calculate like this. Or you can calculate like this. You calculate 1 by 1, or you can use 0.857. Now from the binomial table you can find, if you are taking binomial table, p of x less than or equal to 3 is this value. Okay, sorry, this value. That is an example. Now we will define mean and variance of Poisson distribution. So mean. So suppose let x follows Poisson mu, then we know that p of x mu is, or PMF is, or p of x is e raised to minus mu into mu raised to x divided by x factorial, where x equal to 0, 1, 2, etc. Now we know that expectation of x is sigma over x, x into p of x. This is p of x. This is equal to sigma x equal to 0 to infinity, or let's not say x into e raised to minus mu into mu raised to x divided by x factorial. So now I can cancel out x. So this is x minus 1 factorial. Now this is equal to sigma x equal to 0 to infinity e raised to minus mu into, if I take a mu outside, we'll get mu raised to x minus 1 divided by x minus 1 factorial. So I can take mu into e raised to minus mu is constant, we can take outside, into sigma x equal to 0 to infinity mu raised to x minus 1 divided by, sorry, x equal to 1 to infinity x minus 1 factorial. So we know that e raised to x is actually, sorry, e raised to y is sigma x equal to 0 to infinity y raised to x divided by x factorial. So here this is actually equal to e raised to mu. So mu into e raised to minus mu into this quantity is e raised to mu. So e raised to minus mu into e raised to mu is 1. So the answer is mu. So therefore mean of Poisson random variable is mean equal to mu itself. Mean equal to mu itself. Now we will define variance. So variance is e of x square minus e of x all square. First we will find e of x square. So that is same as, okay, e of x square can be written as e of x into x minus 1 plus x, which is equal to e of x into x minus 1 plus e of x. Okay, so now I will find this e of x into, already we know that e of x equal to mu. X into x minus 1, by definition this is sigma over x, x into x minus 1 into p of x is e raised to minus mu raised to x by x factorial. So range is 1 to etc. So this is equal to sigma over x equal to 0 to infinity. I can cancel out these two, and e raised to minus mu raised to x divided by x minus 2 factorial. I can write it from 2 to infinity. So this is equal to, which implies I can take mu square outside and e raised to mu outside. So mu square e raised to mu into e raised to minus mu into sigma x equal to 2 to infinity mu raised to x minus 2 divided by x minus 2 factorial. So mu raised to x minus 2 divided by x minus 2 factorial, this is actually equal to e raised to mu. So we will get mu square into e raised to minus mu into e raised to mu. So this is equal to mu square. Therefore, e of x square is equal to mu square, that is this, plus this quantity mu. Therefore, variance of x equal to e of x square minus e of x all square, which is equal to mu square plus mu minus mu square. This and this get cancelled. Therefore, answer is mu. Thus, mean and variance of mean equal to mu and variance equal to mu. So, both mean and variance of a binomial random Poisson random variable is mu itself. So, now let us do a problem, and we can conclude today's lecture by doing this problem. So, listen carefully. Solution. Let x the number of flaws on the surface of a randomly selected boiler of a certain type. Have Poisson distribution with the parameter mu equal to 5 and given. So this x is number of flaws on the surface selected boiler type, and given that x follows Poisson mu is 5, x follows p of 5. Therefore, p of x equal to, we can write sigma x equal to 0 to infinity e raised to minus mu is 5 raised to x divided by x factor. Sorry, here there is no, where x equal to 0 1 2 etc. E raised to minus 5 raised. Now first we will calculate p of x less than or equal to 8. So this we can get from the binomial table, sorry, Poisson table. The Poisson table here. So we have mu equal to 5. So this is mu 5 and less than or equal to 8. Mu is 5 and 8. So this quantity is 0.932. So the answer is 0.932. So that is the answer. Now if we want to calculate p of x equal to 8, so this is actually equal to, so I want to calculate 8. So I want this. So this I can written as p of x less than or equal to 8 minus p of x less than or equal to 7. So p of x less than or equal to 8 is minus p of x less than or equal to 7. We can calculate from 0.67. This is 7 and we will get here 0.867. 0.867. So the answer is 17 and 0.65, 0.065 is the answer. Or ഇതല്ലെങ്കിൽ എങ്ങനെ ചെയ്യാം? P of x equal to 8 can be also do by using this formula, that is e raised to minus 5 into 5 raised to 8 divided by x 8 factorial. These are both are same. So now you can do this problem and also do these two problems. Okay, complete this problem. I will send this question in your WhatsApp too, and you do this problem. And next class we will discuss more problems. Okay. If you have any doubt, you can ask me. Otherwise, we can wind up. നിങ്ങൾക്ക് ഡൗട്ട് ഉണ്ടോ? ക്ലിയർ അല്ലേ? Okay. So I will share this question in your WhatsApp.